Hi, everybody. I'm Bob Collum, and welcome to this next edition of Human Landing Site Study Hangouts, or HLS2 Hangouts, a joint presentation by NASA's Human Exploration Operations Mission Directorate and the Science Mission Directorate here at NASA headquarters in Washington, D.C. Today's briefing on where we land, how we land, builds on the conversations that started at the first Human Landing Site Workshop for Human Missions to the Surface of Mars, which was held in October 2015 in Houston, Texas. Before I introduce today's presenters, let's get to know our HLS2 Steering Committee co-chairs, Ben Bussey and Rick Davis. Ben is the Chief Exploration Scientist in NASA's Human Exploration and Operations Mission Directorate, and Rick is the Assistant Director for Science and Exploration in NASA's Science Mission Directorate. Ben, Rick, any words?
No, Jeffrey, I'm particularly looking forward to this one. I think it's going to be really interesting to see how the technology associated with landing will narrow down the interesting places for science and resources that we need to look at.
Rick, anything you'd like to add?
No, just welcome everybody, both everyone watching and also our great speakers. This is really a major topic for trying to figure out, how much latitude and range potentially we can handle, and that's a key question, obviously, coming out of the HLS2 workshop. So it'll be really great to hear everyone's thoughts and ideas. Thank you.
Thank you. Now let's introduce our presenters. Joining us from the Langley Research Center in Virginia, we have Michelle Monk. Michelle is the System Capability Lead for Entry, Descent, and Landing, and will address different EDL architectures and design options. Hi, Michelle. Joining us from Johnson Space Flight Center, we have Steve Hoffman. Steve is an engineering specialist with the Aerospace Corporation and will review the current approach for future human Mars missions being studied by NASA and its implications for where these human crews could land and work on Mars. Hi, Steve.
Hello.
And joining us from Kennedy Space Center, we have Robert Mueller. Robert is the Senior Technologist at the NASA Kennedy Space Center Swamp Works, Mechanical and Space Systems Engineer, who will discuss the challenges associated with landing and launch of large human-rated spacecraft, payloads in excess of 20 metric tons, on the Martian surface. Hi, Rob.
Hello.
Feel free to ask any questions for the presenters in the live chat on our YouTube page, and we'll answer them during the stream. And with that, let's jump right in. Over to you, Steve.
Okay, thanks. Let me do a mic check, make sure I'm coming across all right. Does it sound okay?
You sound just fine, Steve.
Okay, then why don't you bring up the first charts?
Ready whenever you are.
Go ahead. I guess let's see. So I can see a small window. Is it going to take the full screen or just the small window?
It's a full screen on the presentation.
Okay. Then go on to the next one. This is kind of a reminder for those of you who have been on these presentations in the past. First reminder is that NASA doesn't have an official program. So everything we're going to be discussing here today are related to the studies that are being done by the people that are speaking today and others that are supporting them. Things could change. Things are likely to change as we learn more about what Mars is like and what we want to do when we get there. A very abbreviated version of how human crews plan to use crews on Mars. Right now, we envision that there'll be multiple crews of about 4 people in each crew visiting the same surface spot and exploring that spot during the course of their surface missions. So what that means is it gives us the advantage of being able to build up infrastructure, very useful infrastructure over the course of time. We don't have to decide all up front what we're going to do. We can evolve or adapt as each one of these crews visits that spot, and we learn more about what it means to live and work on the surface. We also envision that surface location to be a spot where we're going to be doing a lot of both science and technology development kind of activities. So we're interested in finding a spot where we're not going to exhaust the potential, shall we say, of having multiple crews visit that spot and doing whatever sort of scientific or technology related activities that we have planned for them. That puts some constraints, I guess, on where we land, and I'll be getting into that a little bit more in the following charts. Also, each one of these crews is going to be supported by several landers. We don't have one lander. Well, we envision the work being done by these crews to be such that we can't put everything we need on a single lander. We have a vehicle that gets them back into space from the surface. We're going to deliver that vehicle with the plans right now are to deliver it with methane only, the fuel only, and we'll make oxygen when we get there. So we're leveraging some of the resources that are available to us. Hopefully we'll be able to leverage more of the resources, but right now we're accepting the idea that we can make oxygen, and we'll investigate other possibilities later on. What that it does to us as far as the landing site is concerned is it means that we have to pick a place where we can land multiple landers for each one of these crews without having any sort of the surface terrain hazards restricting how close together we can get these landers. We don't want to have them landing tens of kilometers or more apart from each other simply because we can't find safe places for them to land. So that's a terrain constraint that we have to take into consideration. We also have our own constraints as far as the vehicles we're using. These are going to be fairly large vehicles. Right now, each one of them is thought to be sized such it can deliver about 20 tons of payload each. So that's significantly more than what the robotic vehicles are doing now. And what that means is that the terminal descent engines that we're going to have on each one of these landers is going to kick up potentially quite a bit of debris on the surface. And both Michelle and Rob will talk about more about that later, but I'll give you just a kind of a preview in the following charts about what that, why that's a concern to us and what we've chosen to do about it. So next one, excuse me, next slide, please. So again, as a reminder, the way we've chosen to explore the surface, since we're sending multiple crews back to the same spot, is something we call an exploration zone. Right now, we've convinced ourselves that we can probably have surface mobility such that we can send these crews as much as 100 kilometers radially away from the spot where they land and have them return safely to that central location where we'll have most of our infrastructure located. We'll be looking for a spot where there are going to be multiple regions that are of interest both scientifically and from a technology point of view, and also from a in situ resources point of view. So as we move forward, looking at our options for where we want to send these crews, those are the kind of general mission objective features that we'll be looking for in this exploration zone. Next one, please. Now, so that's kind of the characteristics we're searching for. We've also constrained ourselves to a latitude zone and an altitude zone that we think our landers using the EDL technology that we think is reasonable for these kind of crews can be expected to reach. So what you see here is our current region or zone of the surface that we're opening up for people to propose places where they'd like to send these crews, these exploration zones. Right now it extends from plus 50 degrees to north to 50 degrees south, and it's at altitudes that are lower than about a +2 kilometer relative to the mean altitude of the or elevation of the surface. And that's so that what you see here is that the upper latitudes and lower latitudes are sort of grayed out, and there's black areas where the altitude of the surface is above that 2 kilometer mean elevation. So that's the places where we've asked people to start looking for places where we put these exploration zones. It's a lot of space, and we've had a lot of we've had one session so far, and we had 47 proposals for where we put these exploration zones, and that's what's on the next chart. Bob, if you'd switch to the next one. This is kind of small, but it's available online if you want to look at it, and you can see how the sites are well distributed across the surface. There's no one popular spot that everybody wants to go to. It's well, there are a lot of different places that people have reasons why they would want to go there. So that's our challenge, is to narrow these down to something that's reasonable, something where we can send a crew, for multiple crews actually, for their own missions, and expect them to have a lot of activities to keep them productive during the time they're on the surface. Next one, please. Now, I mentioned that these engines that we have are going to put some constraints on us. This is the Morpheus vehicle at a test at the Kennedy Space Center. This vehicle is about a 3.5 meter tall vehicle, and it has a single engine on it, a 24 kilonewton engine on it. The engine that the landers that we're envisioning will have about 8 engines on them. Each engine will be about 4 times as powerful as that. So you can imagine 8 engines all contributing to that kind of a debris situation, or potential debris situation. And that causes us to be concerned about how close we can have these landers get together. Remember, we want to have them close but not too close. And these large engines, again, depending upon where we have them land, anything that's loose on the surface is going to get kicked up and thrown radially away from that landing spot. Similarly, when we have this vehicle lift off, it's also going to kick up debris. So if you could play the second video, this is the same Morpheus free flyer with the same 24 kilonewton engine. Our ascent vehicle for the cruise will have multiple engines. Again, that'll be 4 times as large as this single engine. And you can see from the close-up that there's a lot of debris that's kicked up just from this small engine, both locally and in that area. And the concern from both of these is that if we're going back to the same spot, it means we have a lot of valuable infrastructure on the surface, and we don't want to have that infrastructure damaged by our own launch, our own ascent vehicles, and our own lander vehicles. So if we go back to the exploration zone again, that square, the white square in the middle, is a central location where we plan to build up this infrastructure over time. And Bob, if you'll go to the next slide, this is what it looks like inside of that white square. Some of the features that we're interested in is some interesting and unique terrain that our guidance system can use to guide on, because we want to land close to the same spot repeatedly. But you can also see the blue circles. This is our current best estimate for how far the engines that we're talking about for these landers can kick up and throw debris on the surface. So we're trying to separate places where landers can reasonably land in terrain that's free of hazards, or as free of hazards as we can make it or find it, but not so close that they will, in landing, that they will throw up debris and damage something that's already there. So this particular spot, you can see we found about 6 different locations where we could put landers that are separated by this roughly 1 kilometer radial distance that we need to have separating them to minimize the debris potential, or debris causing damage kind of potential. The yellow dot that you see in the middle is what we've told the landing people that we want to have is the accuracy for reaching that surface. That's about 100 meters in diameter. And so our plan is to be able to draw an X on the surface, if you will, and have the lander find out where that X is and land within 100 meters of that spot. And so given that we can land with that kind of accuracy, then we can put this separation distance between our landers and be reasonably confident that we're not going to damage any of our own equipment.
Hey,
so
Steve,
Yes.
This is a question for you. How solid is our understanding of the mechanical properties of the regolith? Understand whether or not that 1 kilometer blast radius is really accurate.
I'm going to let Rob get into that. He's worked with a fellow that's done some of the experimental work that we're basing this on. So if you can hold that thought, Rob's going to cover that in more detail in a little bit. So let's see. So this would be our going in position of some place that we think is reasonable. It's got the kind of terrain features that we're interested in. It's got several places where we could land vehicles, because remember, we have to have several of these landing at the same time to support a single crew. But yet they're not so, they're close enough, but not too close. So Bob, if you'll go to the next slide, please. So this is how that particular site our city plan, if you want to think of it that way, would look, how we'd utilize that space. We'd put the habitat, much of the habitation facilities in the center. We'd also put our power supply in the center. In this particular case, we're looking at a nuclear power source for the sort of the base power to supply, the base level power to supply most of what's there. And then surrounding that, we have places where other landers can arrive and depart. So to the right, we have our ascent vehicles. It's called the Mars Ascent Vehicle, and that's the one that would take the crews back into space. And to the left, we have a place where the one-way landers, cargo and crew, can land and still be far enough away that they're not going to damage with their own kicked up debris the habitation and power facilities that we've located there in the center. These landers, once they've been used and once we've stripped or salvaged whatever we can that's useful from them, we're not as concerned then about landing close to them. So the fact that you see just 2 ascent vehicles and 3 cargo landers there doesn't mean that that's all we can ever land. But it does indicate the general area where we put multiple landers of this type for each one of the crews that's going to be exploring this area. And I think Bob yeah, that's my last slide. So with that, I'll turn it over to Michelle, who can talk more about the actual mechanics or systems that will be used to get these vehicles down to the ground.
Okay, thanks. You all saw the challenge that Steve gave us as the landing system community to hit that little yellow dot. So I'm going to talk about some of the architectures that we're looking at to assess whether or not we can do that. But first, let me go back in history a little bit and kind of put into context how large of a challenge this is. So next slide, please. Okay, and can you click one more time, Bob? All right. So on this chart, you see some of our past Mars missions that you're probably all familiar with, and our science objectives down around the bottom: follow the water, explore habitability, all the time preparing for future human explorers. And so, you know, our what I call modern era of Mars exploration with robotic missions started with Pathfinder in 1996, and we've had a number of orbiter assets that help us with our communications relays, and they're also giving us long-term data and great images of the Mars surface and its environment. But none of these has been larger than about 1 metric ton. And you heard Steve mention that to support human crews, we're going to have to land multiple payloads of about 20 metric tons. So we are increasing by an order of magnitude ×2 in our landed capabilities. So we're currently studying different configurations for entry, descent, and landing that would support our first missions. You may have seen out in the literature some other concepts, and there are some by commercial industry that are looking at more of the farther term or colonization types of aspects once we really get our in situ resource utilization and assets fully utilized. But today I'm going to focus on our current NASA study, which is the yellow box sort of in the middle right of the screen. Next slide, please. I wanted to show you how our landing footprint has progressed through our landing missions. We're improving each time, so that's a great start. And to get to the current state of the art, we've made some significant system changes. If you look back at the Viking ellipse, that was about 280 by 100 kilometers. So that's quite a wide area where you might encounter several different types of terrain. Pathfinder did a little better than that. And most of these improvements in the early years came through our navigation state at Mars entry. When we hit the atmosphere, we know better where we are to start with. And then starting with Curiosity, we actually allowed the lander to guide itself during the hypersonic or the highest speed portion of the trajectory. And so we employed that method that will also be used on Mars 2020, which is pretty much a carbon copy in terms of the entry, descent, and landing system to Curiosity. But it will have a couple new features to improve our footprint, including a range trigger on the parachute. Right now, the parachute is triggered on kind of an altitude or dynamic pressure parameter, but this time we're going to be looking at the range to the target and deploying the parachute on that criteria. So we expect that to shrink our footprint a bit more. And in addition, we're using terrain relative navigation. So we'll be using an optical camera to look at the surface as we approach our landing site, and we'll compare what that camera sees to an image of the site that's stored on board the lander. And that's only possible because we have such great images from the Mars Reconnaissance Orbiter. And so you see from the figure that these two implementations are shrinking our footprint quite a bit for Mars 2020 down to about 10 by or 12 by 8.5 kilometers. But that's still a far cry from a 100-meter diameter or 50-meter radius that Steve wants. So how are we going to do that? We're going to be using integrated guidance, nav, and control with improved velocimetry and hazard avoidance sensors on the landers to pinpoint ourselves to that landing location and make sure we don't land on top of other assets that we've already deployed. Now, the ability to steer your vehicle to this precise landing spot is really very dependent on how you're approaching the landing site and what the capabilities of your vehicle are. So if you go to the next slide, this first shows what the 4 landers are that we're assuming we have to land. And as Steve said, this is all in kind of study mode, but we're really looking at this problem at a higher level of detail than we ever have before. In past years, we've just kind of flown what we call a black box. That was literally a black box. But now the surface systems are getting better defined, and we have pretty detailed models of those configurations, so we can actually fly those on realistic trajectories in computer simulations. So I won't go through all the details here, but you see the lander 1 through 4. These payloads assume a 10-meter diameter launch vehicle fairing on the Space Launch System. We assume the crew of 4 is staying for 300 days. So if you're familiar with orbital mechanics lingo, that's a conjunction class mission. And you see the lander 1 takes the rovers and the logistics module. Lander 2 takes the ISRU and the ascent vehicle. Lander 3 takes the rover and more logistics. And then Lander 4 is when the crew finally comes down. Next slide. Now, of course, the mass of our systems are entry, descent, and landing systems that are used to land those big payloads have to ripple back all the way through the whole architecture back to Earth and Earth launch. And so our objective is to get that 20 tons of payload down for the least mass possible. And really that comes down to using the least amount of propellant and structure. Here are 4 of the different types of in-space propulsion architecture options that are being considered. We have solar electric, we have a hybrid solar electric and chemical, there's an all chemical, and then of course a nuclear thermal option. And these all have their pluses and minuses, their different costs, and their different development timelines. And so that's all factored in at the top level of our architecture assessments. Next slide. And now I'll show you some details of the 4 entry, descent, and landing systems that we're considering at this time. You'll see in this table the 4 different shapes, the vehicle dimensions, the launch mass, which is inside the space launch vehicle, how much would we need to lift off the Earth, the entry mass, which is that mass at the top of the Mars atmosphere, the ballistic number, which is just a ratio of the mass to the frontal area of the vehicle. So that tells us kind of whether it's going to dive down like an arrow or if it's going to come in a little more gradually. And then our lift to drag ratio, which is a measure of the amount of control authority or how much we can really steer that vehicle. And so the capsule is a 10-meter diameter capsule. You can see that it's assumed to be very high heritage. It looks a lot like some of the things we've already flown at Mars. The mid-Oliver D vehicle is kind of a derivative of the shuttle, but it has no wings. It has a flattened bottom to maximize the drag through the thin Martian atmosphere. You can see it's about 22 meters long and kind of squished in terms of an ellipse cross section, about 7 or 8 meters in diameter. Then we have 2 deployable options, the Adept, which is the adaptable deployable entry and placement technology. And that's sort of like an umbrella. So it would open up before entry. Actually, this one opens up at Earth, and you can verify its integrity, and then it provides you a large drag area once you get to Mars, but it still fits inside the 10-meter diameter launch vehicle. So you see that for the Adept and the HIAD, the hypersonic inflatable aerodynamic decelerator, those diameters are 16 to 18 meters, and that's because they were folded up during launch and then they deployed before entry. And that helps us get a lower ballistic coefficient, fly a little bit differently. So you can see from these 4 concepts, the capsule is kind of the highest mass because it takes that aft body covering in the back over the payload. The HIAD and Adept are much lighter because they don't have that structure in the back. The payload is exposed. That's why we need to make sure the forebody or the aeroshell is big enough to protect our payload through entry. Next slide.
Quick question, Michelle.
Sure.
From Eric Heller, are all of the landing systems being considered automated, or will the astronauts have control as with the Apollo landers?
That's a great question. We are assuming they're automated because the majority of the landers will not have crew on board and they'll have to land themselves. And even the ones that do have crew, which is 1 out of every 4, we have to assume that the crew is deconditioned from their long ride out to Mars. Okay, next slide, please.
That's what I was trying to
Okay, I'm just going to go through these very quickly. On the left-hand side of each of these charts is kind of a bottom side and oblique view of, so you can get a little better sense of how these vehicles look in 3 dimensions. And then also on the right-hand side is what we call the concept of operations, or the EDL sequence. And so for the capsule, you can see that we come in, start entry. We have a powered descent initiation where we turn engines on about Mach 5 at 10 kilometers altitude. And then we need to turn that vehicle over so that it's vertical. And then we use 8 125 kilonewton engines at 80% throttle to give ourselves a little margin. And then we touch down. So one of the things I didn't mention yet is that that Mars atmosphere is so thin and these vehicles are so large and heavy that we have determined that parachutes are not a viable alternative for landing. So we will be using propulsion to land, which we were going to do anyway in terms of the subsonic descent and landing, but we found that we can turn those engines on higher in the atmosphere at a higher Mach number supersonically and get down to the surface in, at a soft and safe manner. So you won't see any parachutes on any of these concepts. Next slide. Sorry, my light just went off. Okay, I'm back. All right, here's the mid-L over D. You can see that it needs to turn backwards to do its deorbit burn. It comes in sort of like the shuttle did for entry to give us that big surface area for deceleration. And then it turns on its engines at about 2 times the speed of sound and an altitude of about 3 kilometers. Then it needs to rotate over, and this one actually lands horizontally. Whereas the payloads and the other 3 configurations, we call them vertical. They're kind of stacked up like they would be in the launch vehicle. You'll see some doors on the back of this vehicle. And so one concept is to have a crane that could unload the payload, or it could come out the back on rails like the ground operations figure you see there in the middle of the slide. So what we're doing with these different configurations is looking at, one, how they would fly and whether or not they have the capability to meet the 50-meter landing footprint requirements. And a lot of that has to do with how they're approaching the landing site and whether or not the sensors have the time and the field of view to access the surface and be able to process in a way that we could guide our vehicle to the right point. And so that's one point of comparison for all of these concepts. Next slide. So here's the Adept. The Adept actually deploys in Earth orbit. You can see that this configuration, if you look on the upper left, is actually not symmetrical. And so that little bit of a fixed flap or kind of off-center type configuration allows us to generate a lift vector. And so that's why it looks like it does. We come in to Mars and do powered descent initiation or turn our engines on, again, at about Mach 3 and an altitude of 8 kilometers. So we're fairly high in these lower ballistic coefficient characteristics. And we have a little bit smaller engines, 800 kilonewton engines this time, and then we touch down again. The next slide. This is the hypersonic inflatable aerodynamic decelerator, which deploys just before Mars entry. Doesn't take very many minutes. We then come in, and you'll see this profile is very similar to Adept because these two have about the same flight characteristics. You'll see us touch down there, and then the inflatable part of the decelerator can be kind of pulled in to allow better access and offloading for the payloads. So right now, this is our lightest configuration. You'll notice on all of these that we need to have some way for the landing gear to get out, and that we are carrying the aeroshells in all cases all the way to the surface. This was a decision because we feel like it's increased risk, and it's very hard to flight test and qualify that supersonic deceleration event. So if we were to try to separate our aeroshell, we'd have the potential for recontact on the way in. And so it's not a lot of mass impact to just carry our shield all the way to the surface. And as you'll see in Rob's presentation in a moment, that the shield may actually help protect us from some of the debris that we may kick up with our very powerful engines. Next slide.
A quick question from Pascal Lee. Given these EDL systems, can you comment on whether one has an advantage or disadvantage in higher or lower altitude locations?
Well, I would say at this point, the Adept and the Hyad are a little more flexible in terms of their landing altitudes. The slide that Steve showed that shows +2 kilometers altitude is going to be quite challenging. Right now, we're comparing all of these to 0 MOLA, or kind of sea level. But the Adept and the Hyad are the two that are the most scalable in terms of increasing your drag area and being able to land at higher altitudes. Okay, and then this slide shows you how these payloads might package in the 4 different concepts and what the heights might be of these vehicles. So that's one thing we want to consider. Is as we come into a terrain, depending on the slope, we don't want to have a very tall payload that's hard to get out of or may tip over on landing if we have an off-nominal condition. And if you click one more time, you'll see that for the capsule concept, we're having a really hard time getting the payloads to fit within that back shell. And so the Lander 3 and the Lander 4, you can see how the payloads stick out beyond the envelope that we want for them. So at this point, we aren't able to package the same payloads within the capsule configuration as the other 3. Next slide. Okay, and now I'll turn it over to Rob to tell you a little bit more about how we're testing and what some of the data we're using to look at this ejecta problem.
Thank you, Michelle. Can you hear me?
We can. I just had one very quick question before we move on from that last slide, which is the ease of getting the cargo onto the surface for the second option as opposed to the Hyad. They look quite different, with one obviously enclosed and you have to pull it out the back of the vehicle versus just getting it off the other two. So I was just curious to the relative difficulties for that.
Yeah, I think you've picked up on what we can do in terms of qualitative assessment right now. That's one of the disadvantages of the enclosed payload. We could look at making the doors larger, perhaps, but they need to be structurally very stiff because this vehicle takes loads in the vertical direction during launch, and then for entry, as you'll see, it lands horizontally, and so that has to be a very robust structure to take loads in those 2 different directions. So that is a complexity with the mid-L over D vehicle.
All right, thank you, Michelle, and over to you, Rob.
Thank you. Next slide, please. I'm going to talk about the L in EDL. It's an acronym that stands for Entry, Descent, and Landing. And we pay a lot of attention to the entry and descent, but we also have to pay attention to the landing portion of the mission. That's a critical phase. So as the lander comes down with retro propulsion on the surface of Mars, there's a point where the rocket engine plume exhaust will interact with the surface of Mars. So the question then becomes, what are the effects of the rocket engine interacting with the surface? What I'm going to talk about is some work done by Dr. Phil Metzger, who used to be at NASA Kennedy Space Center and is now at the University of Central Florida. And in 2009, this is a paper that I'm quoting, he did a lot of work here at Kennedy Space Center, both experimental and modeling, with computational fluid dynamics, conventional calculations, Navier-Stokes equations, and also the interaction of the high-pressure gas flow with granular materials, which is the picture you see in the middle is actually a small solid rocket motor firing into a granular material test bed. And the granular materials had different layers of various colors so that you could see the effects of the rocket engine interacting with the surface. And so the various columns you see there are the one labeled D is on the far left, and that's the actual rocket engine firing into the surface. And then the other three are previous tests that have already been fired where the granular material has collapsed and filled that hole again. So what we see when we do this analysis is a large amount of interaction between the fluid gases and the particles eroding a crater. And this is different than the moon. When you're on the moon, you're in a hard vacuum. When you're on Mars, you're in a soft vacuum. And so there is an atmosphere on Mars, but it's not a substantial atmosphere. We call that a soft vacuum. But it's enough to make a difference in the way that the plume interacts with the surface. And whereas on the moon, you would have a very flat pattern where the exhaust is reflected about 3 to 5 degrees off of the horizontal and radially outwards. On Mars, what you see in this computational fluid dynamics diagram on the upper left here, you'll see it has a collimated effect where the gas goes down and then does a U-turn at the bottom of the hole and then erodes the particles in that channel on the way up again. An analogy to this would be taking a garden hose and pointing it directly down into the soil, and you'll immediately end up with mud in your face. And so this is exactly what's happening here, is the fluids are going down, being channeled around at the bottom and then directed at the bottom of the lander. And so the first thing that will happen is you will get ejecta. Particles will be ejected towards the bottom of the lander. Now, Michelle referred to the shielding, and so we will need some kind of shielding on the bottom of these landers to protect from these effects of ejecta. The second thing that's going to happen is the particles will be ejected horizontally in a horizontal vector, and that's the diagram on the upper right. And so the question earlier was, where does the number 700 meters come from? It comes from this analysis. And so it's only as good as this analysis is, and the analysis is only as good as the data that it is anchored with. So we certainly need more data and more analysis, but this is a good first attempt at understanding the issue. So what's interesting is that the larger particles are up to 10 centimeters in diameter, and they don't go as far. And then the smaller particles are predicted to be about 3 millimeters in diameter. They're predicted to eject about 700 meters distance at 43 meters per second. Now, as engineers, we tend to not be very well calibrated as to the effects of momentum interchange. So 43 meters per second is over 900 miles an hour, and that's a high velocity. So if you have small 3 millimeter pebbles hitting you at velocities in excess of 900 miles an hour, that's a high potential for damage on any kind of assets that are existing in the vicinity. So this is why we need to pay attention to this problem, is that you will have a ballistic effect of existing rocks and pebbles that are on the surface of Mars being ejected out in these horizontal patterns. Next slide, please. Again, back to Rick's question of can you believe the analysis? We do have some data from the Mars Science Lab, and this is a paper that I've quoted there, which was released in 2015, a study that was done on the quantification of plume soil interaction and excavation due to the sky crane descent stage. Now, the sky crane was used for many reasons, but one of the reasons it was used was to avoid the plume interaction with the surface, because in fact now the lander is hovering and you can lower the rover payload without actually landing on the surface. Then the sky crane stage flies away and you've avoided the problem altogether. And so that was the design intent of the sky crane. In fact, the rocket plume did hit the surface, and you can see these 4 shallow craters called Hepburn, Sleepy Dragon, Burnside, and Goulburn. This is evidence that there is substantial rocket plume interaction with the surface. And bear in mind that this was from the sky crane, which was quite far above the surface. So if you actually touch down on the surface, this effect will be much worse and magnified. So in summary, on the landing part, the rocket plume will interact with the surface if you use retropropulsion. There may be another way of landing on the surface where you shut off the engines early, or you could swivel the engines outwards and vector them so they're canted to the side, and that could be a possible solution. You could also mount the thrusters at the top of the vehicle, such as the Hercules concept. So there are other solutions, and we're looking at those, and we encourage the community to come up with new solutions. But there's one more piece of this. Sometimes I call it EDLL, because we have not only the landing, but also the launch. And during launch, there's a different effect. There's an ignition overpressure, and this is commonly seen on any launch here on Earth. And that's why we have the flame trenches and the deluge and sound suppression systems. There's a large pulse, an ignition overpressure pulse when you light the engine. And this is the acoustic energy and the energy from the chemical propulsion interacting with the ground, and it creates an ignition overpressure pulse, and that is also significant and must be taken into consideration in a launch and landing scenario. And so these kind of effects are commonly seen on Earth. In fact, in the Morpheus video that we just showed, there was a problem initially with the ignition overpressure pulse, and we ended up in that project building a flame trench in order to mitigate the problem of the ignition overpressure pulse. So I would just like to emphasize to the community that this is a problem and an issue that needs to be studied, and mitigations have to be devised. And that's all I have.
So we have one comment from an Arthur P, who points out that 43 meters per second is actually 96 miles an hour, not 900.
I'm sorry, my mistake. 96. That's I did do the conversion yesterday, but it just goes to show that we don't think very well in metric.
Yeah, but it would still sting. I mean, that is still quite fast.
Yeah, thanks for that correction. I appreciate it.
I did a follow up on what you were, and I open this to both you and Steve. Given kind of the dangers associated with these high velocity particles, is there an advantage to looking for a more solid landing surface, either natural bedrock or something that we build?
Well, that is the current thinking. I think Steve can get into this because he was involved with those architecture studies. But right now, the current thinking is that you would land on bedrock and take advantage of a naturally occurring terrain. But we can't be guaranteed that we have bedrock at all the interesting sites.
And the first time we land, it's I mean, it's a chicken and egg problem. The idea of building, improving your landing spot is an attractive one, and it might be something that we evolve into. But the first crew and maybe the first several crews may not have that luxury. So we have to look at the end of the spectrum where we really don't have much in the way of improvements when we get there. So yes, looking for something that's more solid, bedrock, if you will. We probably aren't going to try and land a dune field, for example. We'll try and land in the spot that has that minimizes the amount of surface debris that we have that we could kick up with these engines. But if you look at the spot, the picture that's up on the screen now, I mean, that was chosen to try and be as free of hazard as possible. And there's still a lot of just loose debris that's on the surface that's going to get kicked up, even if there's a substantial amount of bedrock underneath, which you can kind of make out at the bottom of the four craters that are there anyway. So it's an issue. It's an issue that we have to pay attention to. It'll be an issue that we have to take into account when we're picking the actual spot where we land these vehicles, and it'll be a trade-off about what's an interesting place to send people, and what are the risks from hazards on the surface and hazards that we create in getting to those interesting spots.
So if I could ask a question real fast. So are we, for Rob and Steve, maybe Michelle too, SpaceX is landing rockets now, right? And if you go to, Atlanta Hartsfield, they're landing very large airplanes there with a lot of civil engineering going on. I guess I would like to know, one, are there lessons learned, and what does that imply for civil engineering going forward? Because most major operations like that actually prep the ground for it. You don't let the need for ground drive where you set up the airport.
I can take that one. The most common technology used for landing pads is refractory concrete. And in fact, that's what we line the Space Shuttle flame trench with LC-39A and LC-39B. It's lined with refractory concrete. And that is a qualified material of choice, and it works. It's extremely heavy. It's not commonly available in space, and it requires maintenance. And SpaceX is landing vertically now, and that is creating more visibility and attention on this issue. Previously, we worked with Maston in the Mojave Desert. They've been landing for years, and they have told us that they have substantial maintenance issues with the concrete landing pads they use, and they are looking for a better life cycle solution for these landing pads. So I suspect that as we enter more commercial operations at airports and military, they also have jet fighters that land vertically now, Harrier jump jets, F-35. So this vertical takeoff and landing is not unique to space, but the solutions are there on Earth. But in space, it requires specialized materials, and those materials haven't been developed yet. And it also requires equipment, civil engineering, construction equipment, which doesn't exist yet. So although we have solutions on Earth, I would say the maintenance could still be improved on. The life cycle cost of a terrestrial landing pad needs to be improved. And in space, we have to completely invent a new field, which is civil engineering in space.
And if I could just add to that, that's one of the reasons why we call these it's not just the scientific exploration that we'll be undertaking for these human missions. It'll be those kinds of civil engineering experiments and development that we envision being part of the responsibility for these crews. So it's something like landing on the beach and setting up your operations on the beach, but then improving your your beachhead over time. And we hope to learn what works best on these kind of surfaces. But those first few crews will have to adapt to the place where they're landing, and our vehicles will have to be able to accommodate these kind of situations until we can make those civil engineering kind of improvements down the road.
Thanks, Steve and Rob. A quick comment from Laura Kerber chiming into the conversation. Bedrock surfaces sometimes tend to be less flat or more rock covered. So sometimes you have to a trade-off between having fine-grained stuff around and having a flat, rock-free spot. Any thoughts on that, or any other comments to add?
No doubt. Thanks, Laura, for reminding us. I mean, it's going to be a trade-off. We know something about how to distinguish between rocky surfaces and dust-covered surfaces. We should probably invest some, I guess, in figuring out how to maybe do that better. But all of those factors, it's not going to be an easy trade-off. There's not one magic solution where this place works and we'll go looking for that one kind of place. We'll have to look at where we want to land for a variety of reasons, and then at that place find the best landing spot that we can use for our vehicles to arrive and depart.
So I think there's also this element of phasing involved. The first time you land is a unique situation where your main concern is protecting the vehicle and the crew, if there's a crew. The second time you land, it's a new problem. You're not only protecting the vehicle, you're also trying to protect any assets that you've previously landed, especially if you're continuously going back to one site to build up a base. So there's various aspects to this, but once you've landed the first time, you can pre-deploy robotic equipment, which could then have various other solutions like building berms and or other creative solutions that robots could implement. And there you could put up walls, berms, you could do various other things. You could even build landing pads robotically. So I think we just need to really look at this as a systems engineering problem and also time phase it so that you can take advantage also on the landing accuracy. And this might be a good place for Michelle to jump in, is what would be the effect of beacons be if you landed the first time, then you would presumably want to land next to the first land or the second time. So how would you achieve that accuracy, and would it help you to have a first lander with a beacon on it?
Yeah, we've looked at that some, but that's something we need to put in the trade space with the configurations that we're now considering. Usually the beacon is more useful if it's off of your approach vector. So off to the side gives you better information, but it may help in some of the scenarios that we're looking at now.
A quick question from Christopher Dreyer. He's wondering if we could use rovers to create a stable landing spot before human crews arrive.
Can you expand on that? Rovers in what way? I mean, we can use rovers as construction equipment. We can grade the surface. We already built a prototype about 10 years ago now. We put a bulldozer blade on the front of the Chariot rover, and we did show that you could robotically grade an area to level it. We didn't stabilize the surface. There was some other work done on Mauna Kea in Hawaii in about 2011 timeframe, 2012, where we did use solar sintering to try to stabilize a basalt granular material surface, and with mixed results. We've also done sintered pavers in Hawaii, where we made molds and we filled them up with granular basalt regolith. and then sinter the papers, then robotically deploy them into a landing pad, also with mixed results. So this is an active area of research on how to create a landing pad. A rover could certainly be used, but it still needs a lot of work.
Yeah, thank you. I think you answered the question perfectly.
And I think that wraps up today's HLS2 Hangout. We'd like to thank our presenters and thank you all for joining us. We encourage the community to continue the conversation. So if you have thoughts and ideas about what knowledge gaps we should address next, please contact us at nasa-mars-exploration-zones@mail.nasa.gov. And as always, send any questions, comments, and feedback there as well. And you can also find HLS2 resources, including presentations, our workshop statement, and these Hangouts on our website. Thank you so much for joining us. Ben, Rick, any final words?
Just obviously a huge thank you to the speakers. That was incredibly interesting.
And this is Rick. I just echo what Ben said, and I also want to thank everybody for joining us. You know, this is really a community thing. If we get ideas, that's every bit adds up to making this a possibility. And I would just add to one thing that Bob said, which is that if you have ideas about this particular topic too, please send them those to us too, because we'll add them into the chat summary that we're building for this Hangout. And that's a way of getting the conversation going even further. So thank you all.